Okay, so let's get started. Welcome everyone. My name is Sophie, I'm from Flowminder, and I'm very pleased to welcome you to today's webinar. So today is the 5th session on the World Bank Global Data Facilities course on Foundation in Mobile Phone Data for Policy, focusing on the design and implementation for mobile phone data initiatives. And today's course lesson is going to be on data quality and characteristics. I'm very pleased to welcome Ayumi Arai from the University of Tokyo, who is going to deliver today's webinar. Over to you, Ayumi, and thank you.
Okay. So good morning, good afternoon, or good evening to everyone. I'm very pleased to deliver this session on data quality and characteristics. Just a moment. In this session, we will start with an introduction to mobile phone data, looking at the key information contained in CDR and their strengths and limitations. Next, we will cover quality consideration, focusing on how CDR data characteristics affect statistical quality and how to adjust to biases. Finally, we will finish with a quality assurance framework, which provides a structured approach to ensuring reliability and trust in CDR-based statistics. By the end of this session, you should be able to explain what CDR data is and how it's generated, and describe its key characteristic and recognize both its strengths and limitations. You will also be able to identify factors that affect the quality of statistics derived from CDR, understand what other data sources can be used to adjust for biases, and finally, describe frameworks for quality assurance when working with CDR data. So let's begin with an introduction to mobile phone data. Mobile phone can produce different types of location data that can be used to study human mobility. What all these data types have in common is that they describe the approximate geographic position of mobile devices, and that they describe the approximate geographic position of mobile devices, and therefore their uses over time. Broadly, there are two main types of mobile phone data: mobile network operator or MNO data, and GPS data. MNO data is generated whenever a mobile device connects to the network. These data come from the activity of devices within the mobile network and are stored by the mobile network operator. GPS data, on the other hand, is generated by smartphone and captured through the application on the device. These data are typically stored by the company that develop and own the software, such as Google and Apple. The insight we can obtain vary depending the type of event captured. For example, mobile money or transaction data can be useful for poverty mapping. In this session, we will focus on mobile MNO data, in particular a form called call detail records, or CDRs. The characteristics and data quality issue you learn here can also be applied to other types of MNO data, such as signaling data and mobile money data. This type of data is especially valuable for dynamic population mapping and study mobility. And it provides useful insights into areas like migration and transport. This table compares CDR data and GPS data to highlight the strengths and limitations of CDR data. One of the greatest strengths of CDR data is the population coverage. CDR data include all subscribers, regardless of the type of devices and application and operation system installed on the phone. This is because CDR data is primarily collected for billing purposes. Mobile network operator use CDR data to identify the area or cell towers to be upgraded and adjusted. The data is also used for improving their service quality and network optimization. This is closely related to the spatial precision and resolution of CDR data. Location information included in the CDR data is cell tower ID, meaning the spatial resolution is approximated at the cell tower level, while GPS data provides the exact device location. Because the cell tower density varies across areas, spatial precision also varies. Then temporal resolution of CDR data depends on the phone usage behavior. The more frequently phones are used, the more frequent the data becomes. The time resolution of CDR data is intermittent, while the GPS data is continuously stored in a constant manner, like every 1 minute, 3 minutes, depending on the user's setting. So, how is CDR data generated? CDR data are generated when a subscriber makes or receives a call, or sends or receives an SMS, and uses mobile data. CDR data is linked to the location of the cell tower that the mobile phone connects to. This means the location information in CDR data reflects the position of the cell tower, not the actual position of the mobile device. The data are routinely stored by mobile network operator for billing purposes and network optimization. Call detail record, or CDR data, include 3 key pieces of information. First, a pseudonymized identifier of a cell calling party. Second, the cell ID, which is identifier of a cell tower. It is important to know that the CDR itself does not contain the geographic coordinates, like latitude and longitude of the cell tower. That information is usually stored separately. Thirdly, the timestamp of the network event. In addition, the data may also include the identifier of the receiving party and the type of network events, such as a voice call, an SMS, or a data session. And finally, please note that the CDR data never includes the contents of the communication. In other words, they don't capture what was said in the phone call or the text of the SMS. Only the metadata about the event is included. Now let's talk about the pseudonymization. Pseudonymization is a process of protecting personally identifiable information by replacing it with a random strings. The important point here is the same original value will always be replaced by the same pseudonymized value. This means that even though we can't see the real phone number, we can still follow the same user across multiple records because a random strings is consistent. For example, a phone number in mobile data might be replaced like something like this long string you can see on the slide, starting with A1, B2, very long text. If we look at the table below, you can see 3 examples: a phone number, an IMSI or IMSI, and an IMEI or IME. These are typical identifier for the CDR data. Each of these original value has been transformed into a long encrypted string. This way, we remove the personal identifiers, but we can still analyze the data securely without exposing the sensitive information. CDR data can contain different types of identifiers, and it is important to understand the distinction between them. First, we have the MSISDN, which is basically the phone number. This is used for billing purposes and for routing calls and SMS. It is assigned to the SIM card and subscriber. Next is a ISMI or MC, or International Mobile Subscriber Identity. This is unique to SIM card itself and identifies a subscriber within the mobile network. Finally, the IMEI, or International Mobile Equipment Identity. This identifier is unique to the physical handset, meaning it identifies actual mobile device. So in summary, the MSISTN relate to the phone number and subscriber, and IMSI is tied to the SIM card, and IMI is tied to the device. There are several important strengths that makes mobile phone data such an exciting source of big data. First, mobile phones are nearly ubiquitous. Globally, penetration rate are extremely high on average. There are more subscription than people, and even in least developed countries, mobile coverage is widespread. This helps fill important gap left by the traditional data sources. Second, the data itself is high quality and highly granular, generated in near real time. That makes it very useful for producing timely insights when up-to-date information is critical. Finally, this data is already being generated automatically by mobile network operators. That means there is no need to design entirely new system or procedure to collect it. Of course, there are also limitations we must keep in mind. Unlike GPS data, the precision of mobile phone data is limited by the density of cell towers. In urban area, this may not matter much, but in rural area, a tower might cover a radius of several kilometers. Another challenge is representativeness. Not everyone owns or use a mobile phone in the same way, and factors such as age, gender, or income can influence who appeared in the data and how they appear. In addition, one description doesn't always equal one individual. A phone may be shared by several people, or one person might have multiple phone and SIM cards. And finally, these data sets are very large, which means they require proper infrastructure and agreements with operator to ensure the data can be stored and processed securely. In the next session, we will focus on quality consideration when using CDR data for policy purposes. What factors affect the influence and reliability of the data, and how we can draw meaningful insights from it. On this slide, let's look at an example of how device location is observed in CDR data. On the left, you can see a table of timestamps throughout the day. This is an example of timestamps of CDR data. Each entry shows the time of the network event and cell tower the device connected to at that moment. For instance, at 6 a.m. and again 6:35, device connect to a cell tower A. Later, around 7:25 and 8 a.m., it connect to tower B. From mid-morning through the afternoon, the device was connected to tower C before returning in the evening to tower A. So now, if you look at the figure on the right, you can see how this looks spatially, and the phone doesn't reveal the exact position of the user. Instead, we only know which cell tower they are connected to. That means mobility is observed as a movement between towers, from tower A to B, then to tower C, and finally back to tower A. You will notice the device is connected to tower A in the early morning and again late at night. This is a strong signal that this tower is near the user's residential locations. This brings us to an important point. Timestamps are one of the key pieces of information in CDR data. Our daily routine are closely related to the time of the day. We usually leave home in the morning, spend time at work during the day, and return home in the evening. At night, most people are stationary at home. Because of this pattern, even though CDRs don't have explicit attributes like home or work, we can use timestamps combined with tower connections to make inferences. Cell towers observed late at night are likely near a person's home, while towers observed consistently during the working hour are more likely near their workplace. So by analyzing the timestamps, we can infer meaningful types of location at the cell tower level. Now, I'd like to introduce a useful concept for understanding network coverage, the Voronoi diagram. A Voronoi diagram divides a geographic area into regions, where each region is associated with the nearest cell tower. In other words, every point inside the given region is closer to the cell tower than to any other. So each region in this diagram is called a Voronoi cell, and it represents a hypothetical area that the particular cell tower covers. You can see that in the figure on the right, the dot marks the cell towers, and the surrounding polygons show their corresponding Voronoi cells. This is a simplified way to approximate coverage. In practice, the actual coverage may vary due to terrain, tower capacity, and technical factors, but the Voronoi cell gives us a good baseline for analysis. One more thing to note, the size of each Voronoi cell depends on cell tower density. In urban areas with many towers close together, the cells are smaller. In rural area with fewer towers, the cell can be very large. This makes Voronoi diagram a powerful tool to linking CDR data to geographic areas. Now, let's look at an important limitation, flows among cell towers and deviate from actual mobility. On the left, we see a Voronoi diagram. The green dots represent the location of cell towers, and the green trajectory shows the mobility we observe from CDR data. Essentially, the device moving from one tower coverage area to another. The black trajectory shows the actual path of the device. You can see how the two trajectories don't perfectly align. The CDR-based trajectory is much simpler, moving directly from tower to tower, while the real path in between is more detailed and may take a different route. This difference happens for two main reasons. Firstly, the size of each Voronoi cell depends on cell tower density. In urban area, where towers are close together, the approximation is more precise. In rural area, however, a single tower can cover a very large area, which makes the observed mobility much less accurate. Second, the accuracy also depends on how often the device generates events or records. If the phone isn't making calls, sending text or using data frequently, fewer observations are recorded, and we only capture part of the movement. So, while flows among towers provide us a useful approximation of mobility, we need to remember that they don't always reflect the exact path people take. Next, so cell tower density is closely related to population density. Where there are more people, operator needs more towers to provide coverage and capacity. That means in urban area, we typically see a high density of cell towers. with so many towers packed into a small geographic area, we can observe mobility flows at a much finer level of detail. In other words, short trips within a neighborhood are more likely to be captured in urban area. By contrast, in rural area, where the population is sparse, the density of tower is also much lower. A single tower may cover several kilometers, which limits the granularity of mobility we can observe from CDR data. Movements that happen within the coverage area of one cell tower won't be visible. With the same reasoning, we just discussed the number of cell towers in an area also determines the spatial granularity of the data. On the left, you see an area with relatively few towers. Each tower covers a large region, so the spatial precision of mobility or population estimate is quite coarse. On the right, there are many more towers. Each Voronoi cell is much smaller, which gives us much finer spatial precision. This means we can observe population distribution and mobility pattern at a much more detailed level. And again, this usually corresponds with population density. Urban areas have more towers, which allow for greater spatial granularity, while rural areas with fewer towers give us only coarse approximation. Another factor we need to consider is location noise caused by frequent tower switching, also known as handover. Tower switching happens for several reasons. It can occur when the signal strength changes, when the network balance load across towers, or even when the device switches between different technologies supported by the towers. So again, let's make a quick poll. Looking at the highlighted person in this slide, you can see the person highlighted by the red circle. Okay. In the figure, how would this person's mobility appear in the CDR data? CDR shows multiple movement between towers, or CDR shows no movement at all. So please note that the person itself is not moving much, but just the cell tower coverage has been changed because cell tower, because of some technical reasons, sometimes the signal strength changes when the network balance load across tower, or when the device switches between different technologies supported by the towers. So even if you are in the same location, you can easily direct it to the different tower because of various reasons. Okay, thank you very much. So the correct interpretation is that from the perspective of CDR data, this looks like the person has changed its location. But in reality, the device may still be in almost the same place, and the change is purely due to network management. This kind of tower switching introduces noise into location data and can create false signals of mobility, especially in area where tower covers overlaps. One way to mitigate this type of noise is by clustering near my cell towers. When towers are very close together, switching between them can be treated as the same location when you apply clustering. This reduces false movement and gives us a more accurate picture of mobility. Then, when working with CDR data, it's important to think who is actually represented in the dataset you are accessing. If you look at the figure, the first group at the top represents people with no mobile subscription. They don't appear in CDR data at all. The second group shows people who are subscribed to other mobile network operators, unless you are working with data from other operator in the country. These individuals are also missing from your dataset. Now, even within the operator you are working with, not all subscribers generate useful data. The shaded icon in the box represents active subscribers, people who regularly make calls, send text, or use data, and therefore generate CDR data. But unshaded icons represent inactive subscriber in this figure. They may have a SIM card, but if they rarely or never use their phone, then they continue little or no information to the dataset. So the CDR data you have access to is only the subset of the population, active subscriber of participating mobile network operators. This is why representativeness is a key issue when interpreting results from CDR data for policy purposes. To better understand who is represented in the CDR data, let's look at an example from Ghana. This chart shows the share of people who use mobile phones across different demographic groups. First, we can see the most phone use is slightly more common among men than women. About 79% of men use a mobile phone compared to 76% of women. Second, usage varies significantly by age group. Among people of working age, mobile phone use is very high, nearly 90% among those who are aged between 23 to 39. But among children under 15, usage is much lower, and among those over 60, about 72% use a phone. Finally, there are differences by locality. In urban area, over 82% of the population use a mobile phone, while in rural area, it's about 70%. So what does this mean for CDR data? It means that while mobile phone penetration is high overall, certain groups like elderly, children, women, and rural residents may be underrepresented. This is important to keep in mind when interpreting statistics or drawing policy insights from CDR data. So when we use CDR data, we are only working with a subset of the whole population. The box here shows a full population we are trying to estimate, but only the highlighted group at the bottom represents the sample we are actually observing the data. This gap between the full population and the sample is what creates bias, and it's something we always need to keep in mind when we interpret the results. To address the issue of bias, one common approach is population-weighted adjustment. This method combines CDR data with other population sources, such as census data, gridded population estimates, or survey data. Here is how it works. First, we estimate the residential population for each cell tower using CDR data and then aggregate these at the district level. Next, we calculate the scaling factor for each district. This is done by dividing the census population by CDR estimated population. And finally, we adjust the CDR derived estimate by multiplying them by these scaling factors. In practice, we can also refine the adjustment further depending on what additional data we have available, such as information on non-users, multiple SIM holder, or different across mobile phone network operator. This helps us align CDR derived statistics more closely with the actual population, improving the reliability for policy use. This slide shows an example of the different data sources that has been used in 3 countries, DRC, Ghana, and Haiti. For CDR, the main operators are Vodacom in DRC, Telecel in Ghana, and Digicel in Haiti. For baseline population, DRC and Haiti rely on gridded estimate like WorldPop while Ghana has 2021 census data. For secondary survey, we see multi-sector needs assessment in DRC and Haiti, and Ghana's household income and expenditure survey, which include both users and non-users. Finally, primary survey have been run in all three countries, micro-census and phone survey in DRC, a national phone survey in Ghana, and one in Haiti in 2023. So key point is that CDR alone are not enough always. So we need census and survey data to correct for biases and make result representative. Finally, let's move on to the quality assurance framework. Here, we'll look at how we can systematically assess the quality of CDR data and make sure that the statistics we produce are both reliable and useful for policy purposes. Before we move deeper into quality assurance, it's important to recognize that maintaining public trust is essential whenever we use CDR data for policy purposes. The UN expert group summarizes this in an article outlining 5 guiding principles. These principles are aligned with UN National Quality Assurance Framework, something that many of you in National Statistical Office are already very familiar with. Trust isn't only about protecting privacy, so quality is also a key factor. If the data isn't reliable, people will not have confidence in the insights, no matter how secure it is. This article also highlights practical examples from Ghana, the Gambia, and Estonia, where these principles were applied when using CDR data. These cases show how it's possible to adhere to quality standards, protect privacy, and still produce valuable insights for policies. These are the 5 guiding principles described in the article to ensure trust when using mobile operator data for policy purposes. First, necessity and proportionality are fit for purpose. Mobile phone data should only be used when it is really necessary and when it provides insights that other data sources cannot. It should deliver timely and relevant information without creating unnecessary burdens. Second, professional independence. Decision about using MPD, mobile phone data, should always be based on scientific and professional standards, free from political influence as well. This independence is essential to maintain public trust. Thirdly, privacy protection. Any data used for analysis must not include personally identifiable information. It should only be used for statistical purposes and always in line with national laws. Fourth, commitment to quality. Processing should follow scientific standards with clear documentation of method, metadata, and limitation. This ensures that outputs are transparent, reliable, and reproducible. And finally, international comparability. By applying international standards, classification, and shared methodology, we can ensure that statistics are consistent across countries, which makes them far more useful for global cooperation and policy making. Together, these 5 principles form the foundation for maintaining public trust in the use of mobile phone operator data. But these 5 principles are not standalone. In practice, they often require trade-off and balancing. For example, necessity and proportionality must always be balanced against quality. Data should be fit for purpose, but also reliable. Privacy protection, quality, and fitness for purpose are closely linked, and sometimes we must balance between safeguarding privacy and providing useful, timely insights. Similarly, our commitment to quality needs to be balanced with strict privacy protection. and professional independence and the international comparability serve as a foundation, while the other principles often require careful balancing against each other. Here I'd like to introduce the quality assurance framework of the European Statistics System, or FAQAF. This framework provides a set of good practices, methods, and tools that can be applied at the different level, the institutional environment level, the process level, and the output level. It serves as a collection of tried and tested practices that support the production of high-quality official statistics. The current version was adopted in May 2019, and it continued to guide European National Statistical Office in strengthening trust, consistency, and quality in their statistical outputs. Building on the idea of a general quality framework, this slide shows how quality assurance can also be applied in a sector-specific way, in this case, for big data. The framework is organized around 3 processing steps: input, throughput, and output. At the input stage, we look at the source, the metadata, and the data itself. For example, ensuring privacy and security, checking log files, and validating data consistency. At the throughput stage, quality is maintained through system independence, quality gates, and steady processing states. And finally, at the output stage, the focus shifts to confidentiality, accessibility, clarity, coherence, and relevance. This step-by-step approach helps ensure that even with complex and fast-moving data sources like CDR data, we can maintain trust and produce output that meets the standard expected for official statistics. Here I explain about the 3 quality gate aligning with the data processing steps. The first quality gate focuses on input data. This is the very beginning of the pipeline. Here, we review the raw data as it comes from the mobile operators. We check for consistency, perform logical checks, and make sure the data is valid for statistical use. If we identify errors or faults, we don't move forward. Instead, we request correction directly from the operators. In most cases, these corrections can be made by the mobile operators. Only once the raw data passes this first quality gate and reaches a stable and clean state, we proceed into the statistical processing stage. Next is a quality gate focusing on processing, or what we call throughput. This step is especially important when we are designing and building the system. There are multiple parameters and settings that can be adjusted, and to get them right, we often need to run several test loops. Sometimes, we often test different settings under multiple scenarios at the same time. After each loop, we carefully review the data and processing logs to decide what adjustments are needed, and if necessary, we refine the method or the algorithm and run the process again. Once the system is stable and producing results are expected, it passes the second quality gate, and we are ready to move on to the next gate. The final quality gate takes place at the output stage. Here, we focus on reviewing the results for accuracy, consistency, comparability, and coherence. The first step is to check that all output tables align with one another and there are no logical errors. We also compare the outputs with reference data. One of the strengths of big data, like CDR, is that it captures fine-grained pattern that traditional survey or administrative data often miss. For example, short-term mobility or daytime population. That said, it can sometimes be difficult to validate these patterns if no comparable reference exists. In those cases, we focus on selecting a particular dataset, geographic area, or even where the comparisons are feasible to strengthen the confidence in the output. To wrap up, here is a quick summary of the 3 quality gates. Quality gate 1 ensures the input data is consistent, logically sound, and valid for statistical use. Errors are detected early and corrected by mobile network operator before we move forward. Quality gate 2, focusing on processing. This is where system parameters are tested, logs are reviewed, and methods are refined until the system is working properly. Quality gate 3 is at the output stage, where we check the final result for accuracy, consistency, and comparability, and validate them against reference data whenever possible. So together, these 3 quality gates provide a structured way to ensure that CDR data can be transformed into quality statistics for policy use. And with that, I'd like to conclude today's presentation. I hope this has given you a clear picture of both the opportunity and challenges using mobile phone data, and how careful quality assurance is essential for building trust and producing reliable insights.
Attendance today, and we're going to leave it there. I hope to see you all soon.